Hello everyone, welcome to my channel Chemical Engineering Knowledge. In the previous lecture we have discussed about the two-film theory. In this lecture we will discuss about the penetration theory. This is another mass transfer theory. It is called the penetration theory. Penetration theory. The penetration theory is proposed by Hebke in 1935. In 1935, this theory is about to the transport of material from one phase to another phase. It can be from gas to liquid, like absorption. It can be from one cube to another cube, like liquid-liquid extraction. It can be from liquid to gas or from gas to liquid. So, suppose an air bubble is rising in a column, in a narrow column. Suppose this is the air bubble. The air bubble, it is rising in a narrow column. So this is a narrow column. So the air bubble is rising in a narrow column. Suppose this is the water. This is the water. This is the water. This is the air bubble. Air bubble. The air bubble is rising in the column. Suppose in fermenter the air bubble can contain oxygen molecule, nitrogen, argon and other molecules. So suppose absorption of oxygen from air bubble to water, like in fermentation tank. In fermentation tank, oxygen is absorbing from the air bubble into the water. So suppose air bubble is rising in a water column, like in fermenter. So air bubble is rising in the water column. Oxygen is absorbing into the water from the air bubble. Now how the oxygen is absorbing into the water? It is proposed by Hebke in first time. So suppose the air bubble, see the air bubble which is rising in the air bubble is rising in the water. Suppose this is the this is the water. This is the water. This is the air bubble. As the air bubble is rising in the water, according to this theory, the fluid element will come to the surface of the bubble, like the fluid element will come to the surface of the bubble. As the fluid element come to the surface of the bubble, the fluid element come to the surface from this position, similarly from this side. The fluid element come to the surface of the bubble. As it come to the surface, first of all the fluid element will come to the surface of the bubble and to surface of the bubble. Then it will attach to the bubble. It will attach to the bubble, like it come from the bulk of the tube. Suppose this is the bulk of tube, bulk of liquid. This is also bulk of liquid, bulk of liquid. So This is also bulk of liquid. The fluid element come to the surface of the bubble from the bulk of liquid. As it come to the surface of the bubble, this is the bubble. As it come to the surface of the bubble, it will attach to the bubble side. And then it will move along with the spherical surface of the bubble. The fluid, first of all, the fluid element will come to the surface. It will attach to the surface. Then it will slide on the surface of the bubble. It will slide on the surface of spherical bubble. At last, it will detach from the bubble. It will detach from the bubble, and again it will mix with the bulk of liquid. Again mixed up. At this time, similarly, in the next time, another fluid element will come to the surface. It will attach to the surface. It will move along on the surface of the bubble. During its movement on the surface of the bubble, there will be a mass transfer from the gas to the liquid surface, and this mass transfer will be unsteady state mass transfer. So suppose the main points in the penetration theory is that this is the air bubble which is rising in the, suppose it is rising in the water. According to this theory, the fluid element will come to the surface. Right? This is the fluid element. Like similar, this is also the fluid element. It will come to the surface from the bulk. This is the fluid element coming to the surface. This is the fluid element which is coming to the surface of the bubble. It will attach to this bubble, surface of this bubble. These will attach to the surface of the bubble. Then when they attach to the surface of the bubble, after attachment they will slide on the surface of the bubble. They will start sliding on the surface of the spherical bubble. This is the spherical bubble of air. So after attachment, these liquid element will move along the surface of the spherical bubble. And as they are moving on, and as they are sliding on the bulk on the bubble, suppose this is the bubble, this is the liquid element. The liquid element is sliding on the bubble. As the liquid element is sliding on the bubble, there will be transfer. There will be a transfer of gas from the bubble to the liquid element. Suppose this is the liquid element. This is the gas. The gas will transfer from the bubble to the liquid element, and in the liquid element the concentration of solute will be increases with the passage of time. So there will be unsteady state mass transfer will occur during the sliding of so there will be unsteady state mass transfer when the liquid element is sliding on the surface of the bubble. So there will be unsteady state mass transfer when the liquid element is sliding on the surface of the spherical bubble. So there are some assumptions of the penetration theory. The first assumption of the penetration theory is that there will be unsteady state mass transfer. Unsteady mass transfer to the liquid element. Liquid element is it come to the bubble surface. Similarly, the second assumption is that there will be equilibrium will achieved is the liquid. Equilibrium will achieved between gas and liquid, or liquid and liquid, or some other two two phases. So in this case, equilibrium will achieve as the liquid element come to the bulk to the bubble surface. So equilibrium will achieve if the gas liquid interface. Equilibrium will achieve at the gas liquid interface. It will be unsteady state mass transfer, and the equilibrium will achieve at the gas liquid interface. And the third assumption is the contact time of each liquid element will be same. The contact time of each liquid element on the surface of the air bubble will be same. Like, what are the three assumptions? What are the three meaning of these three assumptions? Suppose this was air bubble, it was rising in the water. From the bulk, the liquid element was come to the surface. This was the liquid element, it come to the surface. So when it come to the surface, it is attached to the surface. When it attached to the surface, after attachment, it is sliding on the surface of the bubble. So when it is sliding on the surface of the bubble, suppose this element is sliding on the surface of the air bubble. When it is sliding on the surface of the bubble, there will be transport of material from the air to the liquid, and this transport of material will be unsteady. So this will be unsteady state mass transfer during the attachment. Suppose this is the air bubble and this is the element which is sliding on the surface. So this is the bubble, this is the liquid element. When the liquid element is sliding on the surface of the bubble, so there will be unsteady state mass transfer. So with the passage of time, the mass transfer will be decreased. So there will be unsteady state mass transfer in the liquid element. So unsteady state mass transfer will be occur. In the liquid element when it is so unsteady state mass transfer will occur in the liquid element which is attached to the bubble, which is attached to the air bubble. So when the liquid element is sliding on the surface of the air bubble, there will be unsteady state mass transfer in the liquid element during its sliding on the when it is sliding on the surface of the air bubble, or when the liquid element is attached to the surface of the bubble, then unsteady state mass transfer will start in the liquid element. The second assumption is that there will be equilibrium exists between the gas. This is the gas and this is the liquid. The liquid element is sliding on the surface. This is the liquid, this is the gas. There will be equilibrium at the gas liquid interface. This is the gas liquid interface. This place is the gas liquid interface. So equilibrium or Henry type law will be obeyed in this at this position. So there will be equilibrium. There will be equilibrium exists between the gas and the liquid. In the gas, the mole fraction is Y, and in the liquid, the mole fraction is is xi, suppose, and it will be a function of some, it will be form a function like this, or some equilibrium function like the Henry law type like function will be obtained. So there will be equilibrium at the gas liquid. This is the gas, this is the liquid. So equilibrium will exist at the gas liquid interface when the liquid element come to the surface of the gas bubble. The third assumption is that the contact time of each liquid element, with the gas bubble will be same. So this is the gas bubble, B is for the gas bubble, and this is for the liquid element. This is L. L is for liquid element. Suppose this is the air, this is the water, bulk of water. It is rising in the bulk. The bubble is rising in the water. So liquid element come to the surface. This is the liquid element. It come to the surface of the bubble. It is attached to the surface of the. It is attached on the surface of the bubble. Now, what will be the contact time? It will attach to the surface of the bubble. Then it will slide on the surface of the bubble. Then at last it will detach from the surface of the bubble to the bulk of liquid water. It will detach from the surface of the bubble to the bulk of water. So what will be the contact time of this what will be the contact time of the liquid element with the bubble? What will be the contact time of this liquid element? What will be the contact time of this liquid element with the when it is what will be the contact time of liquid element with the gas bubble? So the contact time is nothing but it is denoted by Tc, and it will be equal to the diameter of the bubble. Suppose this is the bubble, this is the diameter of the bubble, this is the air bubble, the whole. The diameter of the bubble is this. So this is the air bubble, this is the diameter of the air bubble, and the so the diameter, it will be the contact time of the liquid element with the bubble will be equal to the diameter of the air bubble divided by the speed of air bubble with which the air bubble is rising in the liquid. So this is the diameter of the bubble, this is the speed of the air bubble or the velocity of air bubble in the liquid with which the air bubble is rising in the water. So the speed of air bubble is nothing but it is meter per second. So speed is nothing but meter per second. So it is length or meter, or it is, suppose it is meter per second. Now we know that diameter is also a distance. So this is the distance, meter divided by meter into second. Second is in time. So this is the contact time. So the unit is also same. If we see to the unit, it will also same. So the contact time is equal to the diameter of the bubble divided by the speed of the or the velocity of the bubble. So it is equal to the contact time of the liquid element with the air bubble. Now according to this theory, the contact time of each liquid element with the bubble will be same, which is wrong, which is not true in this theory. So in the coming theory, the contact time of each element is not equal. Some element will come to the bubble, it will stay for less time. Another element of liquid will come, it will stay for long time. So it depends on the diameter of the air bubble, it depends on the speed of the air bubble. Some bubble are the speed of some bubble in the water is will be small. The speed of some, the rising speed of some bubble in the water will be less. So it depends on speed, diameter of the bubble. But in reality, the contact time of each liquid element with the bubble is not the same, which is this is the main drawback of the penetration theory, because every element of every liquid element cannot stay for the same time with the bubble, with the air bubble. So this is the main drawback. Some element can stay less time, while the other element can stay long time. it depends on the density of the bubble. It can be depend on the size of the bubble. So for example, if some element will detach from the air bubble if they are young, while the other liquid element will stay for long time. So it depends on the bubble dia, the density of the liquid water. So in the coming theory we will which is the surface renewal theory. In the surface renewal theory this drawback is solved, and in the surface renewal theory it is said that there will be not contact time, but it will be average time. In the penetration theory we are using the contact time, but in the surface renewal theory we are using the average time. In the penetration theory we using contact time, while in surface renewal theory we will use the average time. And as we know that some element will so if you know that some element will stay for less time, suppose it will stay for less time, or suppose it is t1, while some element will stay for a higher time. So we will take their average and we will use the average time, not the contact time, as we are using in this penetration theory. So in surface renewal theory we will use the average of time. So what are the mathematical form of the penetration theory? The penetration theory is like the unsteady state heat transfer in the semi-infinite solid. In the two film theory we know that the mass transfer coefficient was directly proportional to the diffusivity divided by length. But in this theory, in the penetration theory, the mass transfer coefficient is directly proportional to the under root of diffusivity. So how can we relate these two quantities? So we will go to some mathematical form. So we know that the mass flux of A, suppose the first postulate of this theory which we have discussed, that the mass transfer in the liquid element will be unsteady. There will be unsteady state mass transfer in the liquid element. So the fixed second law will be written for this postulate. So it is Ca by dt, diffusivity of A and B. This is the this is the second law. So suppose this was the gas bubble, so this is the liquid element, it was attached to the surface, it is rising in the water, it is some diameter, this is the liquid element. Now the liquid element, there is unsteady state, this is the liquid element, this is the gas. This unsteady state mass transfer in the liquid element, So this unsteady state mass transfer is given by the fixed second law. Now if you don't know about fixed second law, please like my video which is given in the description of this video. You will derive this equation from the fixed first law. So this is the fixed second law which shows that the concentration is a function of time and also a function of position. So suppose this is x is the position, and this is the time. With the passage of time, this is the x position, this is the concentration. This is with the passage of time. Suppose this shows time, and this shows the position, and this shows the concentration. So concentration is a function of time and position. Similarly, the final form of the fixed second law, we will simplify the fixed first law, and we will use the similarity variable, which is nothing but x divided by 4 into diffusivity of A and B into time. We will use this similarity variable in equation number 1. This is equation 2. We will use the similarity variable in equation number 1. We will convert the partial differential equation, the second order partial differential equation, into the first order partial differential equation. We will then solve the first order partial differential equation by separable of variable method, and from this we will solve the second order partial differential equation. The final solution will be equal to CA minus CAB, CAI minus CAB is equal to 1 minus error function of similarity variable, which is nothing but the complementary error function of the similarity variable. Now, what is the error function? You can also watch my video related to the complementary error function in the heat transfer lecture, which is given in the description of this video. So, the final form is Ca minus Cab. The Ca is the concentration at any time. This is the concentration in the bulk. The Ca is the concentration at the interface, and the Cab is the concentration in the bulk. It is equal to 1 minus error function of the similarity variable. Now, what is the error function? The graphical form of error function is this is the similarity variable. This is the error function of the similarity variable. Similarly, this is the similarity variable. This is the complementary error function of similarity variable. So the error function of 0 is 0. The complementary error function of 0 is 1. So these are two different functions, and the sum of error and complementary error function is 1. So again, this complementary error function plus error function will be gives 1. So if you have not watched the video, please watch the video about error function and complementary error function, which is given in the description of this video. You will completely understand the this video. So this is the final form. This is the final form of the this is the final form which gives us the relation between concentration and the distance. So distance and time, because the similarity variable contains both quantity. Similarity variable is x divided by diffusivity and time into 4. So this is the time, this is the x direction. So it contains two independent variables. We combine two independent variables into one quantity. So the final form of the similarity variable is the equation number 2. Now we can also find the flux of A at time t will be equal to by dAB dCA by d dx, so that x is equal to 0. Now what is the d? Now this can be further equal to the flux of A at time will be given by dAB dCA by dx. So now, and this is the x is equal to 0 position. That means if this was the bulb, this was the bubble, and this is the liquid, this is the liquid, this is the liquid. So at x is equal to 0, this is at this position at interface. X is equal to 0, it will be interface. So similarly, when x tends to infinity, then the concentration of A will be, and x tends to infinity, the Ca will be equal to Cab. This is one of the conditions. Similarly, when x is equal to 0, then Ca will be equal to Cai, concentration at the interface. When x is equal to 0, this is x is equal to 0. So Ca is equal to Cai, concentration at the interface. So this is the, similarly when time is equal to 0 and t is equal to 0, Ca will be equal to Cab. It means that when time is equal to 0, a fresh liquid element come to the surface. At time t is equal to 0, a fresh liquid element come to the surface, which is, and the concentration of component A in the fresh element which come to the surface, the concentration of component A in the fresh liquid element which has just come to the surface is Cab. which is present in this bulk region. So the flux of component A at time t is dAb dCA by dx at x is equal to 0, which can be further simplified, and the final equation will be given Na diffusivity of A and B, phi contact time, concentration of A at the interface, concentration of A in the bulk. These can be obtained from the boundary and initial condition. So please watch my video on the heat transfer in semi-infinite medium. You will get this relation. You cannot obtain this relation directly, but this is the final equation. Now, with the passage of time, the concentration in the liquid will be decreases. This is the liquid. This was the case. With the passage of time, the concentration in the liquid element is increases with the passage of time. So after long time, the concentration gradient in this liquid element will be 0. So it is better to use the average mass mass flux. So the average mass flux. So this is the instantaneous mass flux with time. Now the average mass flux of component A in the liquid element will be given by Na average. Average is equal to 1 divided by contact time, from 0 to contact time, dAb by contact time, and contact time Na T, and this is the dt. Now this NAT is given in equation number 4, which will put NAT in this place. So we will get Na average mass flux is at time t is 1 over t 0 to Tc, and the NAT is given from equation 4, which is dAb phi t. This is the Tc, and this is the Cai minus Cab and 2dt. Now we know that this is 1 over Tc, this is the dAb, this is the phi, this is the under the root, this is the concentration at the interface, concentration in the bulk, and this is the time, this is also the time. So we will apply the integrate only to the time, not to this phi and this dAb. These are constant, these are also constant. So apply the integral sign to 1 over 2 dt. After integration of this term, we will get Na average mass flux at time t is equal to 2 dAb phi into Tc. This is the diffusivity of component A and component B. This is the phi, which is 3.14 rational number. This is the Tc is a contact time, which is obtained from the diameter of the bubble and the velocity of the bubble, the rising velocity of the bubble, which is nothing but the contact time of liquid element with the bubble. So, and this is the Cai into Cab, and this is the average mass flux of component A in the liquid element. So, according to penetration theory, the mass flux, the mass transfer coefficient is directly proportional to the dAb divided by phi into the contact time under the root. So this shows that the mass transfer coefficient is directly proportional to the under root of diffusivity of A and B, and inversely proportional to the contact time. As the contact time increases, the mass transfer coefficient will be decreases, because the solubility will be increases with the passage of time, the gradient will be decreases with the passage of time. The mass transfer gradient will be decreases with the passage of time. As time increases, gradient will be decreases. As the gradient decreases, the mass transfer coefficient will be decreases. So this is all about the penetration theory. Similarly, the average mass transfer coefficient, which gives us that average mass transfer coefficient is directly proportional to the diffusivity of A and B divided by pi into Pc under the root into 2. Now forget about this number, B CAI minus CAB. These are only gradients. So we are just gradient. So in this case, mass transfer coefficient is directly, in this case the mass transfer coefficient is directly proportional to the square root of diffusivity, while in the film theory the mass transfer coefficient was directly proportional to the diffusivity of A and B to the power 1. In this case, mass transfer coefficient is directly proportional to the diffusivity of A and B to the power of 1 over 2. So this is about the penetration theory. If you don't understand how can this equation can be obtained, how the final equation can be obtained, if you don't know how the final equation is obtained, then please watch my video. I recommended you that please watch this the video. You will understand the complete concept of the mass transfer in the semi-infinite medium. So if you are new to the channel, please like and subscribe. Thanks.